Heat effects in gas absorption. Heat effects are one of the most important considerations in the design of gas absorption towers. This is because heat effects cause temperatures to vary along the length of the tower because the solute gas strongly depends on the temperature. Heat effects may or may not be neglected. When heat effects are neglected, the computation is much more simple. However, when it cannot be neglected, the computations become much more difficult. Y.T. Shah, author of Gas Liquid Solid Reactor Design, concluded that most of the systems involving chemical reactions, temperature effects are not very important. This is based on reviews of literature concerning heat effects in systems which involves gas-liquid reactions. Some systems wherein large amount of heat may be released includes compensating effects, which decrease the effect on the rate of absorption. For example, increase in temperature of solution tends to increase the rate of chemical reaction and decreases the solubility of the reactant at the solvent interface. Examples of these are where the compensating effects can occur are the absorption of carbon dioxide in amine solutions and the absorption of carbon dioxide in sodium hydroxide solutions. Some examples of systems wherein heat effects cannot be ignored is the absorption of ammonia in H2 in water and the dehumidification of air in concentrated sulfuric acid. Heat effects that may cause temperatures to vary from point to point in a gas absorber are the heat of solution of the solute, which includes the heat of condensation, heat of mixing, and the heat of reaction. This can lead to a rise in the liquid temperature. Number 2, the heat of vaporization or condensation of the solvent. Number 3, the exchange of sensible heat between the gas and the liquid phases. And number 4, the loss of sensible heat from the fluids to internal or external cooling coils or to the atmosphere via tower walls. The approaches in dealing with heat effects from a designer's point of view are the following. Number 1, the addition of internal or external heat transfer surface. This is done to remove heat from the absorber. Number 2, treatment of the process as if it were isothermal by arbitrarily assuming that the temperature of the liquid phase is the same everywhere, followed by the addition of a design safety factor. Number 3, employment of the classical adiabatic model. This assumes that the heat of solution manifests itself only as sensible heat in the liquid phase and that solvent vaporization is negligible. Number 4, using semi-theoretical shortcut methods derived from thorough calculations. Number 5, employment of precise design procedures. This requires the use of a digital computer. Conditions that cause major heat effects are the substantial heat of solution and the absorption of large amounts of solute in the liquid phase. When pre-screening, we can opt for simpler methods of designing. However, in the final design on computations, a more thorough and precise method is required. Operating variables. Number 1 is the operating pressure. Increasing the operating pressure leads to an increase in the separation efficiency significantly. Number 2 is the temperature of fresh solvent or the entering solvent. This has only The temperature of the fresh solvent or the entering solvent has only a slight influence on the degree of absorption and the internal temperature profiles in an absorber where the heat effects are caused by heat of solution or solvent vaporization. This is governed by internal heat effects or the temperature profile in the liquid phase. Number 3 is the temperature and humidity of the rich gas. Cooling and constant dehumidification of the feed gas has many benefits to an absorption tower. High humidity limits the capacity of the gas phase to take up latent heat, which makes it unfavorable to absorption. This is the downside of high humidity. Number 4 is the liquid to gas ratio. Increase in the liquid to gas ratios result in less strongly developed temperature profiles, and as the L over G is increased, the operating line moves away from the equilibrium line and the tendency for more solute to be absorbed per stage increases. This, however, has a compensating effect wherein more heat is released at each stage, which leads to increase in plate temperatures and an upward shift in the equilibrium line. As the L over G is decreased, the capacity of the liquid phase to absorb solute decreases as well, and the concentration of solute builds up in the upper parts of the absorber, causing the point of highest temperature to move upward in the tower until finally the maximum temp develops only on the topmost plate. Number 5 is the number of stages. The addition of plates has no useful effects on the separation efficiency when heat effects combine to produce an extended zone within the tower where little absorption takes place. These difficulties can be resolved by increase in solvent flow or introducing strategically placed coolers, cooling and dehumidifying the inlet gas, and or raising the tower operating pressure. Next, we will hear about equipment considerations and design methods from